Imagine the laws of physics not as rules governing matter, but as lines of code running on a universal processor. Recent theoretical work and experiments strengthen the case that information is conserved in quantum processes, one major clue in the black hole information debate, though the story is still developing. In 2025, researchers studying entanglement argued that preservation of information could even help explain cosmic mysteries like dark energy, not as a hidden force, but as the operating cost of computation itself. If that's true, then understanding matter and energy means starting with something deeper: information. From atoms to bits, the new foundation of reality. For most of human history, reality was explained in tangible terms, things we could touch, weigh, and observe. Rocks, rivers, stars, and fire all seem to fit into a framework of matter and energy shifting from one form to another. This machine-like picture of the world guided centuries of science and engineering. But over the last several decades, a new perspective has gained ground, one that sees the underlying fabric of reality not in terms of objects or energy, but in terms of information. At first glance, information seems abstract, even out of place in physics. Most people think of files on a computer or numbers on a page. In physics, though, the word carries a stricter meaning. Information is the quantifiable set of distinctions between possible states. It defines how systems evolve, how particles interact, and even how large-scale structures emerge in the universe. Many physicists now argue that information is not just a tool for describing physical processes, but a foundational quantity, on par with matter and energy. One of the most concise ways this idea has been expressed is in John Wheeler's phrase "it from bit." Wheeler, one of the leading physicists of the 20th century, suggested that everything physical, from particles to fields to the very geometry of space-time, may ultimately arise from binary distinctions, the yes or no decisions that form the logic of computation. When he first introduced the idea, it sounded speculative. Yet today, with advances in both quantum theory and information theory, the notion that reality might be grounded in bits looks far less like a metaphor and more like a serious framework for physics. To see why, consider how modern physics treats information. Unlike mass or energy, information might seem intangible, yet it too can be measured. And in processes governed by quantum mechanics, it appears to follow strict laws. For instance, in entanglement, two particles that are linked across space always keep their informational content balanced, even as they shift states. The individual states may change, but the total information describing the system doesn't disappear. This conservation suggests that information, like energy, must be accounted for everywhere in the universe. This principle shows up in some of physics' thorniest problems. Perhaps the most famous example is the black hole information paradox. When matter collapses into a black hole, its physical details vanish from view. For decades, that seemed to imply information might be destroyed. But research increasingly indicates the opposite, that the total informational content is preserved, encoded perhaps on the black hole's boundary itself. This is closely tied to the holographic principle, which proposes that all the information about a region in space can be described on its surface. Physicists even use concepts like the Bekenstein bound to quantify this idea, showing that the maximum information capacity of a region scales not with its volume, but with the area of its boundary. This connection between space, entropy, and information hints at something very concrete. Information has physical limits and measurable consequences. Shifting to this perspective forces us to rethink older mechanical models of the cosmos. The classical view treated particles as tiny, solid objects moving like billiard balls across a cosmic table. But quantum mechanics showed that such a picture is incomplete. At small scales, particles are not rigid pieces of matter but probability distributions, constrained by rules of superposition and entanglement. And those rules themselves are best described not as movements of miniature objects, but as transformations of information. Quantum equations read almost like instructions for updating a system's informational state. The probabilities adjusted, the history recorded, nothing lost. This helps explain why quantum technologies feel so different from classical machines. A quantum computer doesn't simulate the behavior of particles as objects. It directly manipulates informational states at the most fundamental level. Qubits can overlap, interact, and recombine in ways that mirror how nature itself operates. Experiments in 2025 showed such systems scaling beyond a few dozen qubits toward hundreds, revealing how quickly informational complexity grows when it is not bound by the strict either-or constraints of classical mechanics. The machines being built now don't just use the rules of physics, they expose them. Seen in this light, everyday matter takes on a new character. The rigidity of a table or the warmth from a stove isn't simply matter behaving mechanically. It's the expression of stable informational arrangements on a macroscopic scale. The patterns of molecules, the bonding of atoms, the flow of heat, all of it results from the way information has been stored and structured through countless prior interactions. Even the apparent emptiness of space may be dense with informational encoding, its vacuum fluctuations reflecting hidden processes running beneath visibility. This perspective invites a shift in how we define what is basic. The proton, the photon, the gravitational field, these may not be the deepest building blocks after all. They may be emergent expressions of a more fundamental substrate, information. What feels like solidity or the flow of energy could simply be the display layer of an underlying computation. In that sense, the familiar world is not an illusion. It's the interface through which informational processes appear to us. When researchers first spoke of the universe as information-based, many heard the comparison as poetic metaphor. But as measurements tighten and theories expand, the metaphor blurs into literal description. Information is not just a label that humans apply after the fact. It behaves like a constrained, conserved element of reality that obeys measurable limits. Many physicists now treat it alongside mass, charge, and energy as central to the accounting of the universe. This shift does not replace the old physics so much as extend it, pointing to a deeper lawfulness beneath the surface. And with this recognition comes a sobering implication. Physical reality might be structured more like a process than a machine. Instead of thinking in terms of parts pushed and pulled, it may be more accurate to think in terms of distinctions updated, records preserved, and informational states transformed. Rather than gears turning in a clockwork universe, reality may operate more like a continuously running program. Its visible outputs the material events we measure, its hidden workings the calculations we can only infer. This idea prepares the ground for the next step. If reality is ordered around informational updates, we need to ask how those updates happen. What kind of logic governs the transitions from one state to another? Classical physics provides one kind of answer, rooted in deterministic outcomes. Yet quantum physics points to another, stranger system of rules that resemble the operations of computation but resist the definiteness of classical machines. The question is whether those rules reveal the true code shaping reality itself. The code of the universe, quantum logic versus classical laws. Classical computers operate on a clear principle. They move ones and zeros through circuits, applying fixed instructions that always resolve to a definite outcome. Every operation is like pressing a switch one way or the other. This binary model has powered everything from smartphones to space travel, but it remains a simplification. Nature at its most fundamental level rarely gives such neat answers. What we observe in the quantum world is filled with uncertainty, overlapping possibilities, and correlations that resist being reduced to tidy categories. This is why quantum computers, though they appear strange at first glance, feel so closely aligned with how the universe already functions. They don't just process information differently, they process it in a way that mirrors the behavior of physical reality itself. In these machines, the fundamental unit of information is the qubit. Unlike a classical bit, fixed as either 0 or 1, a qubit can exist in a mixture of both states simultaneously through a principle known as superposition. If a classical bit is like a coin that has landed heads or tails, a qubit is like holding the coin in mid-spin, where all possible outcomes are still present. The mathematics of quantum mechanics allows calculations to unfold across these possibilities at once, with a definite outcome appearing only when the system is measured. This may seem counterintuitive, yet it is consistent with how electrons, photons, and atoms behave. Superposition, however, is not the only feature that sets quantum logic apart. Quantum systems also make use of entanglement, an effect that standard computers cannot reproduce. When two qubits are entangled, their states are joined so tightly that a change in one is reflected in the other instantly, even across vast distances. No signal is sent between them. Instead, their shared description encodes the correlation directly. Einstein once dismissed it as spooky action, but repeated experiments have established it beyond doubt. Entanglement is not just an oddity, it is a resource. In technology, it enables qubits to coordinate at levels far beyond what separate bits could ever achieve. In physics, it may even play a role in the very structure of spacetime itself. Either way, the lesson is similar. The universe at its core operates through linked outcomes, not isolated events. This parallel between physics and technology raises an important question. Why should the rules that make quantum computers viable line up so closely with the rules that describe nature? Classical computing is a human invention, built on human choices. Quantum computing, by contrast, takes its operating principles directly from what experiments with matter revealed. The probabilistic way these devices function was not imagined, it was observed. Building a quantum computer is not like forcing the world to behave according to our models. It is like constructing a system that runs on the same principles reality already uses. Each demonstration of a quantum algorithm that outpaces a classical one carries technological meaning, but it also signals something deeper. The logic of nature is computational. The differences stand out more when compared side by side. In a classical computer, flipping a bit erases its previous state. The information is lost, like chalk wiped from a board. In quantum systems, prior information lingers within superpositions and entangled states even as they update. This mirrors how physics treats information itself, where evidence increasingly suggests nothing is ever truly destroyed. Energy may transform, particles may scatter, but information seems conserved. Quantum processors echo this by allowing data to interfere with itself in structured patterns no traditional system can imitate. They do not discard states, they preserve and recombine them. Probability further distinguishes the two logics. Classical programs guarantee the same output every time when given the same input. A quantum program instead provides a range of possible results, distributed according to precise mathematical weights. This directly reflects physical experiments, such as observing electrons hitting a screen. You can predict the overall statistical pattern, but never the exact placement of one event. Quantum computers turn this seeming unpredictability into a feature, making uncertainty a working part of the calculation. Nature does the same. The very laws of physics are written not as rigid certainties, but as probability distributions shaping what can occur. By 2025, this once theoretical framework is visible in engineered machines with hundreds of functional qubits. Google's Willow processor, operating with 105 controllable qubits, combined with laboratory demonstrations of below-threshold error suppression, shows that superposition and entanglement are no longer just metaphors. They are tools now being used at scale. These advances confirm how close engineered quantum devices come to reflecting the rules physics already follows. Still, it is important to be precise. Quantum processors have not replaced classical ones. They show massive speedups in very specific tasks, especially problems involving vast possibility spaces, but they are not universally superior. The real significance lies in how they highlight the fact that our technology is beginning to exploit the same code the universe runs on. The implications grow sharper as systems scale. Classical computing is still indispensable for everyday calculations, but it operates on premises that ignore the richness of probabilities and connections inherent in quantum logic. Quantum computing steps closer to how reality evolves. When thousands of possible outcomes are tracked together, when entanglement spans hundreds of qubits, the computations begin to resemble not a tool outside of nature, but a managed version of nature's own activity. Each experiment reminds us that classical algorithms approximate reality, whereas quantum logic seems to embody it. This matters beyond the lab. The things classical logic fails to fully capture, the stability of atoms, the coherence of wave functions, the strange persistence of entanglement, are all explained naturally within the rules that quantum devices are built to obey. The fact that researchers can manipulate these effects rather than just describe them suggests that reality and computation are bound by the same constraints. Our machines are not simply interpreters of hidden laws. They are participants, playing out those laws in engineered form. Seen this way, quantum processors are more than advanced tools. They may be small-scale demonstrations of the very same informational logic that spans from subatomic particles to galaxies. They rely on coherence, correlation, and probability, not certainty. And every time a specially designed quantum program demonstrates results beyond the reach of classical algorithms, it points to the possibility that the cosmos itself runs on similar operating principles. Progress in the field shows how quickly this analogy moves toward practicality. With larger, more stable systems, the boundaries between what is engineered and what is natural continue to blur. Each improvement reflects reality back to us in more detail, as if scaling up processors is akin to scaling up our ability to model pieces of the universe from the inside. The closer these devices get to representing physical processes with fidelity, the less they seem like computational novelties, and the more they resemble windows into how existence processes information. This trajectory sets the stage for the next leap forward. Once quantum machines begin working with thousands of stable, coordinated qubits, they do more than handle bigger datasets or faster searches. They begin to approximate the scale of complexity required to represent patterns within the natural world itself. And it is at this point, as designs push past thresholds long thought years away, that the resemblance between quantum processors and the universe's own structure becomes much harder to dismiss. IBM's 1,000-plus qubit leap and what it reveals. In late 2024 and into 2025, IBM announced a step that the field of quantum computing had been anticipating for years: the achievement of more than 1,000 functioning physical qubits on a single device. Their Condor processor, unveiled at the end of 2023, contained about 1,121 physical qubits, marking the first time a system crossed that benchmark. It is important to be precise here. These were physical qubits, the raw building blocks that hold quantum states. They are not yet the error-corrected logical qubits that researchers ultimately aspire to build. Those remain a future goal. Logical qubits are stabilized, fault-tolerant units that can perform long computations reliably, and scaling them into the thousands is still on the horizon. But even so, surpassing 1,000 physical qubits is a turning point, because it shows that densely packed and controllable arrays can function on a scale large enough to explore problems far beyond toy models. IBM has been careful to emphasize this distinction in its roadmap. Alongside Condor, the company introduced the Heron processor with around 156 qubits, designed not for sheer count but for lower error rates and improved reliability. The lesson was straightforward. Bigger arrays matter, but stable and error-resilient designs are essential for useful computation. IBM's forward-looking plans, such as its proposed Startling systems in the late 2020s, focus on combining these approaches, using error correction methods like quantum LDPC codes to build genuinely fault-tolerant machines. This makes clear why passing 1,000 physical qubits is both impressive and preliminary. The milestone demonstrates feasibility, but the long-term target remains logical qubits that can sustain calculations without collapsing under noise. Why does this matter so much? Because in quantum systems, scaling has an exponential effect. Adding qubits is not like adding extra horsepower to a car engine. In classical machines, doubling computational parts means roughly doubling performance. In quantum machines, each added qubit multiplies the possible states the system can explore simultaneously. Just 2 qubits hold 4 states, 10 qubits describe over 1,000, and at the level of 1,000 qubits the state space is unimaginably vast. This explosion of combinations mirrors the complexity encountered in natural systems, whether in molecules, stars, or networks of neurons, where rich correlations appear when certain thresholds are crossed. IBM's Condor leap opened a foothold into that terrain, not by analogy, but by scaling technology into ranges where entanglement and interference start to resemble naturally occurring patterns. The debate about usefulness versus fragility has surrounded quantum computing for decades. Early critics argued these machines would remain too unstable ever to outperform classical systems in practical domains. Yet engineering has repeatedly shown ways to stretch coherence further, extending how long qubits can remain intact before noise overwhelms them. Layering error suppression and correction onto physical arrays begins to yield stability that lasts long enough for non-trivial computation. This is significant beyond engineering. It hints at the same kind of order that physical law itself seems to maintain across cosmic scales. The IBM device does not prove that reality computes, but it narrows the gap between laboratory quantum information processes and the physical behavior we study in nature. The resemblance is worth noting, not as a claim of equivalence, but as a reminder of how closely our tools now echo the operations of the systems we seek to understand.